All right, line A5, learning task 8. We're going to take a look at connection of three-phase power factor correction capacitors, where we place them on the system and what the reasons for them are. When you went through second year, you would have covered power factor correction. And the reason that we do power factor correction is because we get the most ideal transmission of voltage. As soon as we have got any sort of a kVAR in our system, VARs, which are going to be that reactive power, our total kVA is going to go up. And when our kVA goes up, that means that our current has gone up, which means that we are going to go and get more line drop, more line loss, and a lower terminal voltage at our load. And in some cases, the kVARs themselves can be so large that it's going to result in, in having to add additional services or add the additional size to capacity of your services that you have on a site. In other cases, what you're able to do is you're able to actually correct that. You can take power factor correction capacitors and you can drop your kVA back down, and it kind of frees up a bunch more room on your system itself. We would like to have a unity power factor. However, there's very few things that actually run at a unity power factor. Things like incandescent lights were great for unity power factor, but those have become more or less obsolete at this point. Electric heat resistance is going to be unity power factor, but a lot of our other loads are going to go and have either a lagging or, in some cases, a leading power factor. Motors and ballast type of lighting to do with fluorescence and with HID lights in particular, are all going to go and have lagging or inductive sort of effects. You can actually get some capacitive kVARs that are going to be created by some of our LED lights. A lot of LED lights, because it's two separate, it's a PN junction, they act as if they were a bunch of tiny little capacitors. So we can go and get a leading or a lagging kVAR, or leading or lagging system, just due to the loads that we have connected onto it. And we want to go and correct that. It's rare to go leading, to have too much capacitance on the system, but it is very, very common for us to go and have a lagging one. And if we do have a lagging one, we're going to go and add kVAR power factor correction capacitors in to go and fix it up. Let's take a look at a system. A system is broken down into three main parts. We're going to go and have the true power component, or the kilowatts of the system. This is the actual useful work that goes to lighting stuff, turning motors, etc. Stuff that we have a deliverable on. Then what we have is we've got another component that is going to be called our VARs, or kVARs, and this is going to be a magnetizing component. It's also known as reactive power. And this is going to just be used to create the magnetic fields, sustain the magnetic fields. We need it for operation, but it takes away from our overall. And it's actually at 90 degrees out from our kilowatts itself. What happens is that these two are going to go and add together. And when they do, we get a total apparent power, or what we refer to as our kVA. The kVA is changeable. The kilowatts are generally going to be fixed inside of a system, but the kVA is going to be changeable by changing the amount of VARs. If I would shorten the amount of VARs, I'm going to have a smaller kVA. It's going to be a smaller hypotenuse on the triangle. I can go and shorten it down more and more, etc., as we go along. And that's what we are going to try and do, is we're going to go and find what we have got for inductive kVARs, and then we're going to go and apply capacitance in the opposite direction to knock that value back. It looks a little similar to this. This would be a similar type of system. Once again, we see that the kilowatts themselves, not affected. We see that we had an original kVAR that was all the way up to here with an original kVA that was all the way out to here. But what we were able to do is we were able to go and take capacitance. We were able to go and knock that inductive kVAR back. And when we did so, we created a new triangle over here. Still delivers the same amount of true kilowatts of power, but it has got far less of my VARs, my reactive power, and it has got a much lower kVA, or total amount of current that is going to be traveling through my lines. This results in less line drop and less line loss. You lose less heat inside of your installation as well. You also don't get damage to things like transformers and conductors as quickly because you aren't overheating them. Three basic methods that we're going to go and use for correcting power factor. Those are going to go and be individual capacitor units, where we're going to go and take individual ones. We're going to connect them across a load. I'm just going to jump back here. Stick an individual cap size to the loads, K-bars, at each individual load. This is going to take time and it's expensive because you're going to have to go to each load, sort out how much capacity you need to go and correct, and then go and connect it on at each one. The next method is a large bank of capacitors, or a centralized bank where you're going to go and have a whole pile of capacitors, not usually just one, but a whole pile of smaller ones that are going to get switched in and out. And in a lot of cases, that's going to be done electronically and automatically by some metering that is going to be continuously reading the system and reacting to it. The best method would be to go and have a combination of individual units and large banks. Stick a centralized large bank to deal with any small fluctuations and the thousands and thousands of tiny loads that you have around your plant, but then put in large individual capacitors on your larger inductive loads, things like gigantic motors that you might have, etc. As far as how these capacitors are built, we can go and connect 3 single-phase capacitors, either in Y or delta ourselves, but it is usually far cheaper for us to go and buy a 3-phase connection that's going to have that connection done already internally. The 3-phase ones are just going to go and have 3 lines coming out the top. You see that over here, T1, T2, T3 on both of these. And then they're going to go and have all of the capacitance, all the capacitive plates and the dielectric in between. All of that will be on the inside. And then they're going to be connected in either Y or delta. Y connections are going to be used, generally speaking, when I have got a high voltage type of installation. And the reason for that is we know that my E phase is equal to my E line divided by root 3. In other words, my phase value of voltage is always going to be lower than my line value of voltage. So if I have got a 25 kV line over here that I'm feeding out to a motor, and this happens in industry, large industry will use 25 kV. If I've got 25 kV to that motor, what I'm going to go and have for my actual Y value on the inside, the phase, are only going to be 14.4 kV. And that is going to be huge when it comes to things like insulation inside and the spacing on the capacitor plates, because now I'm dropping from 25 kV down to that 14.4 kilovolts inside there. This is why we like to go and use Y type of systems when we're dealing with high voltage. If I'm dealing with a lower value of voltage, but with a high current type, let me just write that out there. High current and lower value of voltage. So, we're maybe 600 volts, maybe 1200 volts, something like that, but nothing too high. But if I've got a very, very large amount of current, and if I need to go and have a massive power factor correction capacitor over there, I'm going to go and make my connection in delta, because that way my current, capacitive current, can be delivered out from both of these 2 phases at the same time to join together to go and become that larger line value of current that we have anytime that we're dealing with delta. Remember that for delta, I line is equal to I phase times root 3. So we're going to go and have a smaller value of phase current inside of here that we're shuttling back and forth, which once again means smaller, more compact units. Okay, let's take a look at connections. There's 4 main positions that we can go and connect it in. First one we're going to take a look at is going to be A, and A is going to be the most effective place for me to go and put a power factor correction capacitor. The reason for that is that any of my K-bars that are generated by the motor coming out of the motor are instantly going to be captured by this power factor correction over here. We're just going to go and shuttle those K-bars back and forth. In second year, we learned about these capacitors and how basically when we've got an inductive and a capacitive load, they're going to go and toss that current back and forth like it's a football. Just, the inductor has it and the capacitor has it, etc. But if I'm only passing that current back and forth over top of these lines, that means all that extra current does not have to go over any of the rest of the lines inside of my installation. This means that I'm going to go and have the lowest value of current coming into my motor, and I'm going to be having the least amount of line loss and line drop to it. However, there is a danger, and that danger for placing it here in A is these overload relays. The overload relays themselves are sized to the motor. They're designed to go and create a bit of heat that's going to trip an element and kicks off that motor contactor. If I go and take out some of that motor current is composed of the bars current. When I go and buy my motor, it's going to go and have its total current based upon the kVA of that motor. So as soon as I take out all of the VAR's current, that means that I'm only left with the true watts, which is going to be lower. So I'm going to go and have to be careful with these, and I'm going to make them smaller. I'm going to have to do this through just doing some testing, running the motor with an ammeter on there, and figuring out what size I should be using. It can be a little bit tricky to do. And because it's a little bit tricky to do, equipment manufacturers don't like us doing it, because there's a chance that we could screw that up, burn out their piece of equipment, and then come crying back to them for warranty. They don't like that. So what equipment manufacturers are going to go and recommend is that we go and place them inside of B, which is this green one that we have over here. This has almost all the same benefits as what we would have for A. The big difference is that it is ahead of my overload relays. So all of my VAR current that is going to be going back and forth between these two is still traveling through the overload relays, which means that those overload relays are going to be able to be sized to their true value that they need. This is usually going to be the one that's going to be recommended by anybody who's in motor control, because that way, if the motor gets changed or anything like that, there's no fancy calculations that are needed. We just size our overload heaters to the motor itself. And generally speaking, from the overload relay to the actual motor is usually a fairly short run. We don't go incredibly long distances from, our control cabinets to the motors if we can help it. Occasionally we might. In that case, we might have to go to that location A for our capacitor, but when we can, we try to keep these things close together. Location C has got special, it has a reason that we have this one over here. Location C is ahead of our motor contactor, right over there. And this is really good for any time where I am doing rapid movements on my motor itself. If I'm going and jogging the motor, that means I'm bumping it on, bumping it forward, etc. If I'm reversing it, that would mean that I'm interchanging two lines. All of that is going to go and happen downstream of the contactor. And so we're going to go and have inrushes, and particularly if we would reverse the capacitor, we can actually really have an incredible amount of damage that will happen to that capacitor. So what we'll do, if we are planning on jogging or reversing, we need to place that capacitor upstream of the contactor. That way it always stays in the same configuration. My line A, B, and C always stays there in the correct configuration. In this case, you would also need to go and have some sort of a starter that's going to go and turn this thing on. So because it's a motor circuit, you would want to go and have something that's going to go and turn on this capacitor whenever the motor itself is called to go and operate. So you might have a separate contactor that's going to be used for that. The last location that we're going to go and take a look at is just going to be what we refer to as feeder correction. That's going to be my D location up over here. That D location would be where I'm going to get a very large bank of capacitors, usually hundreds of tiny small capacitors, but then I've got a whole cabinet full of contactors and automatic sensing relays, current relays, and things like that that are going to be continuously reading what's going on inside of my mains. So this power factor correction capacitor is made up of many small ones that is going to be monitoring my mains over here. We'll stick a couple of ammeters around those, and then it is going to be switching on and off through little contactors inside of here, multiple different capacitors as they're needed to power factor correct for the system. These are usually going to be spec'd by one of the actual power factor correction companies out there. There's lots of companies that just specialize in this because you need a lot of specialty equipment. The meters to do the testing for this, etc., get really, really expensive. So in a lot of cases, if you do need to go and look at a plant and fix the power factor off of it, what you can do is you can contact these companies out there, and then they will go and send you out a really, really fancy ammeter that's going to go around all three of your main lines. And it's also going to go and have some voltage probes going to all the different lines. And it's what we call a power logger. And you're going to place this thing on, and you're going to leave this thing running for like a week. And at the end of that week, You can then come back, you're just going to unplug the thing, pack it back up, and you mail it back out to these companies. They take all the data, they read it all, and then based upon what they're seeing, because they're going to go and have trends, they're going to see how the kVARs are, changing or staying the same throughout the day, etc. They're going to be able to tell you which of their specific capacitors they recommend that you go and place in. To be honest, you're safest to go with that type of a route. Trying to go and do all the engineering and track all of this down yourself is a massive, massive undertaking. And if you get it wrong, you can be in the hole for, tons of hours and tens of thousands of dollars of equipment. Last thing we need to talk about is safety with capacitors. Capacitors are just a temporary storage of charge, which means that if that charge is stored and you pick this thing up, there's a good chance that you could discharge it on yourself. As a result, these capacitors need to go and have a discharge resistor. And usually you'll see that on these large caps. If you see one of these large caps, you'll see the two terminal blades, and then across there's going to be a high impedance resistor. High enough, it's going to be in 50 k ohm, 100 k ohm or something like that, that it's not always going to be draining current from your load. You don't want to be, running a lot of current if you don't have to. But it's going to allow this thing, whenever power gets shut off, to go and, whenever the power gets shut off, it is going to allow that current to drain from one side of the cap over to the other. Usually they're going to go and require at least 1 minute for low voltage power factor correction capacitors, but anything that is going to be high voltage is going to be up to 5 minutes off of these. Just be careful. If it's got caps in it, make sure that you allow this thing to discharge, particularly some of the pieces of equipment that you don't understand has caps in it. Variable frequency drives, VFDs, a lot of motor drives have capacitors in them, either for power factor correction or as temporary DC stores of charge. Be very careful around these things. Give them some time to go and run through their discharge before you touch them. As far as sizing for your capacitors, operate them correctly at their rated kVARs. If a capacitor has got a different frequency listed on it, if you take a capacitor that is rated for 50 hertz because it's European to use on an American 60 hertz, it is going to completely change the kVAR rating. You cannot be going and doing that. Use them at the proper voltage and the proper frequency. And then last of all, never go into a leading power factor. If you oversize your caps and you push all the way into a unity power factor, your terminal voltage will raise on all of your inductive loads and on your transformers, which means that now you're going to have over voltages throughout your entire plant. Just don't do it. The other main big reason is that BC Hydro on industrial properties monitors power factor. And if you go into a leading power factor, BC Hydro will assess some massive, massive fines against your company. So don't do that. Treat the caps with a little bit of respect and give them time to go and discharge before you touch them, and make sure you're operating them at the correct voltage and the correct frequency.